Alrighty, so hello everyone. Thank you for being here. Welcome along. My name is Chris. Today I'm going to be talking a little bit about normal surfaces and hopefully motivating a little bit about why and how we might want to use a computer to do topology, whatever that means. So our goal, how can we use a computer to answer topological questions? In order to get there, few things I want to clarify. First of all, what is a question? What is a computer? How can we represent topological data in a computer? Kind of an essential point, that one. And how can a computer answer these questions? So I'm being a little bit silly here. Some of these questions will take much more effort to answer than others. Hopefully that's pretty evident. But let's get right in there. Questions I've put in quote marks deliberately here because I do think it's good to clarify what actually I mean. And I want to look at this through the framework of a decision problem. Okay, so we have some kind of question, again, asked with some defined input and exactly two possible outputs that we could have. Okay, so we have a yes or a no. Think of it as true or false if you like. But we are really just deciding, for our purposes, some property of some object. Okay, an example, if I input a knot, is the knot the unknot or is it not the unknot? Fairly common question that you're going to ask yourself if you're dealing with knots. If you're dealing with other kinds of topological objects, other kinds of questions arise. We will hopefully see one of those later on. Next, what do I mean by a computer? To give you the silly definition, something the Church-Turing thesis applies to, but really something which will take an input, execute some kind of algorithm, not going to get into what that means, and answer a decision problem. Okay, we want to be able to actually hand this work off to something that is not a human. Okay, computers are great for many things, namely sitting there, putting attention to some task that a human does not want to sit down and just do for hours and hours on end. The beauty of a computer for this type of problem is that we can just tell it to enumerate every single possible thing, every way that we can try and untangle this bit of rope and answer whether it's actually the unknot, that sort of thing. So the main thing we need to get through here is how we actually talk about these objects in the realm of a computer. Here's a solid torus, or at least I've told you it's solid, you can't see the inside, so maybe it's just the outside. For our purposes, we're going to be thinking in 3 dimensions or lower today, so how are we supposed to represent that in a computer, right? Obviously, I've been able to do it because it's there, right? It's on the screen, but all I have is an image, right? I've got a picture, I've got a PNG specifically, which is just a bunch of pixels that are a certain color, right? That's not actually very useful if I want to do topology on it, if all I have is a flat 2D image. So what else can we do? Well, we can think of this as being some kind of parametric surface, if we like. We can write down some equations that tell us a mapping from R2 onto surface, onto patches of this thing. If it's solid, then we can do essentially the same idea, right? And that's all well and good, but we want something that's actually going to be a more tangible representation of this solid object, somehow using only a finite amount of information, okay? Specifically, a finite amount of information that will fit inside my computer. It's all well and good if I can write it down with, 10 trillion bits, but that's still going to be difficult to fit into my laptop. So let's start by defining a simplex. We need a basic building block. I can see we've got people who are very enthusiastic. That's very good. An n-dimensional simplex, for today's purposes, convex hull of n+1 affinely independent points. A face of a simplex is the convex hull of any subset of those points. Okay. Practically, oh no, I've also given you another definition here. And then we can merge these simplices together. Merge is a bad word. We can put these simplices together, glue them together into a simplicial complex, where we get a collection of simplices which obey a couple of rules. Okay, so we need that every face of every simplex is also in the complex, and we want that for every pair of simplices, their intersection is a face of both of them, okay? That obeys some nice rules, it gives us a nice structure, and yes, question?
Just trying to read that second one.
Yeah.
That's basically saying that not this.
Yes.
Right?
So exactly. So if I have two simplices, I can't have them going over like this. They can't like cross and through each other, if we like. Yeah. So that's definition of a simplicial complex. Okay. For our purposes, though, today, a simplex is any of these things. We don't need any more than that. If you want to live in dimension 4 or higher, please feel free to do so, but I'm not going to today. So we can have a vertex, which is the zero-dimensional simplex. We can have a line segment or an edge. We can have a triangle, and we can have a tetrahedron. Hopefully, there are going to be tetrahedrons again later on. Hopefully, these are legible as being three-dimensional objects. If we get problems with visualizing what's going on, let me know, but I'm hoping that all the drawings should be simple enough. But these are all of our simplices. And we can stick them together. So here is an example of a simplicial complex. So we have sort of two tetrahedra that have been stuck together along one triangular face here. We have another tetrahedron down here, which meets this one at exactly this vertex. There's a triangle stuck on at a vertex up here. Over here we have an edge, and these two triangles have been stuck together along an edge. Okay. So this does obey the rules that we saw earlier. Specifically, the thing that we want to watch out for is that we have, every time we've glued these two objects together, these two tetrahedra, for example, this triangular face is a face of both tetrahedra. Okay. Over here, we've met at our vertex, and that vertex is a face of this tetrahedron, or you can view it as being a face of this edge, or a face of the triangle. They all count, and all the rules are still obeyed everywhere along here. Yeah.
So, sorry, just to clarify again, not this, but also not this.
Yes. Very good point. So we have this edge meeting at this vertex. If it were to meet anywhere else along this edge, except of course for the other vertex, if it met anywhere along here, then the intersection of these two edges would be one point, which would be a vertex of this edge, is not a vertex of this edge. Okay, and so that would not count as a simplicial complex. Okay, because that point is not a face of this edge. Cool. All right. So useful example there. And temporarily, we can say that a triangulation of a manifold is a locally finite to get away from annoying infinite things, but really we want to only consider things that are going to be at least probably compact. There'll be adjectives. We can largely ignore them for our purposes. We want a locally finite simplicial complex such that the manifold and the simplicial complex are homeomorphic. Okay, we saw some details of this last week with Christian's talk. I'm going to gloss over a little bit of that. The point is we can stick together these simplices to make something which is topologically the same as our manifold that we care about. Yeah. So the locally finite condition here is saying that for any vertex in the triangulation, it is a member of finitely many tetrahedra, or finitely many anything. That makes sense? Cool. For our purposes, we're going to limit ourselves to tetrahedra. Of course, this could be high dimension. Cool. This definition does work really nicely. It gives us some nice theorems. So theorem from Rado, 1926, of course, every 2 manifold is triangulable, and every 3 manifold Moisey, or Moy, I did not look up the pronunciation, I really should have, alas. Anything in dimension 2 or 3, we can get a triangulation. Lovely. So surely we're done. Almost. We definitely have something where, assuming that our manifold is not going to be infinite and we need infinitely many tetrahedra, so long as we're dealing with something that's nice, we can write down a list of tetrahedra. We have all of their vertices. We can tell where each thing is being glued onto each other thing, and everything should work. That's a finite amount of information, not too hard to write that down in a computer. And indeed, I promised a physical prop, triangulation of a sphere, or if you like, triangulation of a disk that I've done some weird torture to. Both acceptable views of this particular object, but we have a bunch of triangles around the surface of this sphere. Hopefully that makes sense and no one's concerned about this particular object. Wonderful. Okay. So, prop out the way. Then we have a look at this thing. For those of us who have seen a diagram like this before, hopefully it's quite evident that this is a cylinder that I've unwrapped. I'm going to identify the two edges with the arrows on them. So you can see that vertices A and B are also vertices A and B over there. And that looks like a perfectly fine triangulation of a cylinder. In fact, second prop, it certainly looks like I can take that, pretend that I've glued pieces of paper together along those edges, and then glue those sides together and get a cylinder. That's perfectly fine. This is definitely a cylinder, but that is not a simplicial complex. In fact, the issue we run into is if we look at this triangle here, ABC, and we look at triangle BCD, the intersection is two vertices. And two vertices are not a simplex. We need that intersection to be a simplex somewhere, a face of one of the other, well, first, a face of both of these, which that is not, and also to be a simplex in the simplicial complex, which that is not. So we run into a small issue. For this reason, using a simplicial complex while it works causes us to be a bit wasteful sometimes with our tetrahedra. Or, well, later tetrahedra, here, triangles. You could, I think, if I remember correctly, fix this issue by flipping this edge and taking it here to here. I think that works. I can't remember. You can do something to flip things around. I'm getting a shaking of the head, so probably not. No. So, oh, yes. So you would get, yes. Yeah, so you can definitely add more triangles and fix this, make it an actual simplicial complex. And I forgot to draw the example of what that actually does, but in any case, to fix this, we need more triangles, which is not great. Yes?
Why is this undesirable as like a triangulation of the cylinder?
It's not undesirable. We want this to be a triangulation. Yeah, so that's what I'm trying to get to, yes. It would be really nice if this is a triangulation of the cylinder. Unfortunately, it's not a simplicial complex, so we're going to need to change our definition somehow. And what we're going to say is that, again, working in the three-dimensional context, I did actually write simplices here. So a triangulation of manifold is going to be a finite collection of simplices. Again, we're going to discard infinity for now. We want a finite collection of gluings between their top-level faces or their facets. So we're taking, for our purposes today, tetrahedra, identifying their triangular faces. Okay. We are not restricting gluings between faces of the same tetrahedron. So if you take one tetrahedron, you want to glue two of its faces together by stretching it around itself, perfectly acceptable. That's totally fine. But we do need to make sure that we line these things up as triangular faces. What that means, working back a dimension now, is that this is a perfectly fine triangulation of a Möbius band, where actually what I'm doing, I've put all of the directions on here. What I'm actually doing is identifying these two edges. And it turns out that that is exactly the same as doing this and, where am I going? There we are. And identifying those edges, except we just need to pretend that this edge has length 0. And then you get a triangle. A bit glib, but you can effectively do that. And then we have a nice efficient triangulation of the Möbius band. We get to only use one triangle, whereas otherwise, if I remember correctly, you need 9 to make it a simplicial complex. So we're saving at least some amount of memory that we need to store. which is useful when you're working with a computer. If you have a very large, complex manifold, then you want to be able to avoid storing more data than you actually need to. So this, again, is not going to obey being a simplicial complex, but it does allow us to still work with everything nicely. We don't have to worry about, what was I trying to say? We don't have to worry about our objects being larger than they need to. Yes?
So this could be a very naive comment.
Oh, good.
This feels like a lot more natural than like simplicial complex. Like why were we wanting to have a simplicial complex calculation first, not just like jump to this?
Formally, a simplicial complex gets you more structure. You deal with things that are, yeah. The point was more to illustrate that with a simplicial complex, you can do all these theorems perfectly fine, but if you want to actually stick it in a computer, then it can be helpful to just reduce the amount of information. The other advantage simplicial complex gives you is that if you obey the rules, then you definitely get a manifold at the end. You can run into problems if you use this more abstract definition where you can write down gluings and sets of tetrahedra that don't actually become a three manifold at the end. You break other things somewhere. I can't remember what the counterexamples are, but there's something. Yeah. Yeah. Again, forget this arrow. I'm not identifying this edge anyway. That's going to become the boundary of the Mobius band. But yes, the point is that for the purpose of being in a computer, the additional work to check if your user gives you this or something, whatever, to check that the thing you've defined is actually a manifold, is not so bad in comparison to the savings you can make, so long as you know what you're doing. So it turns out to be a trade-off that makes sense. Yes, Michael.
Is the condition of being triangulizable going to be in any crucial structure?
I think so.
So you're not gaining any more out of moving to triangulability in terms of like what can express?
No, at least no. Yeah.
Even higher than
Cool. All right, we're on board. Lovely. Okay. So as I was mentioning just before, we can now, with this revised definition, triangulate the solid torus with one tetrahedron. In a fairly cursed way, I must say. It has one vertex, and the three edges are all loops that do... I don't understand properly how this actually works. I read several explanations. The gist of it, apparently, take a Möbius band, essentially flatten out two faces of this tetrahedron, and then stick that, well, two tetrahedra onto the Möbius band, and that somehow makes this work properly. It took me hours. I could not figure out what was going on. So if anyone else has better intuition, please let me know later. But we can do it, which is nice. Again, we're making savings for something like this, not actually terribly many tetrahedra, but if you have something which is essentially just a lot of tetrahedra, a lot of tori stuck together, you end up saving many. So you get benefits out of this, even if to visualize it's not the easiest. So I said we were going to get to normal surfaces, and now we can define them. Hooray. We're going to assume that we have some kind of, for our purposes, we're going to say compact, three manifold, has a triangulation, okay? We already know they all have triangulations, so we're perfectly good. And then we're going to take S to be a surface properly embedded in M. We call S a normal surface if for every tau in our triangulation, the intersection of that surface with tau is a normal disk, okay? So all I've done is moved the problem one step further. Yes? That's a great question, Evie. I've prepared an answer for you already. So it's a lot of words. In a moment, you'll get a definition by picture, and that will be a lot clearer. But formally, we have all these details. The idea is that we are interacting with our triangulation nicely for this definition of nice, which means that we want to never be tangent to our faces of the tetrahedron, and we want to not sort of cut at a vertex or on an edge or something like that. So again, formal details. The normal disk has to be cutting through this tetrahedron, having its boundary on the triangular faces of the tetrahedron, and either making a triangle where you cut off one vertex or making a quadrilateral where you cut two edges opposite each other apart. The picture, I think, is clearer. Here are all 7 types of possible normal disk in one tetrahedron. Okay? Yeah.
Probably going to similar to understand, but immediately, why would we be looking into something like this? Why is an object like this equal to?
Exactly. Now, it was a choice of whether to motivate it first and then get to what the definition has to be, or go the other way around. And I think this way is going to be more useful. Later on, yes, we will get to the point of why these actually matter. I couldn't quite come up with a reason why you decide to invent this first, other than
Is there a surface level, like immediate, like on this feature, like look out under this feature? Is there anything I should be looking to throughout this talk about these surfaces?
Not particularly. One source that I cannot remember where it was. I should have mentioned as well, the idea of normal surfaces is originally due to a German guy called Kneser, whose son is the guy who defined Kneser graphs, and whose dad also was a mathematician, and all of them were very Nazi. So that was just an unfortunate fact. But you have the idea of these first came up. He was just kind of the first person who went and said, I'm going to try and study a 3-manifold via looking at surfaces that are embedded in them. And it turns out normal surfaces, you can do a lot. So that's become the thing you study. Harkin, who will come up later, then took the idea and formalized it properly and developed the theory, and it's continued since then. No. The idea is to study the 3-manifold via whatever these surfaces can tell us, which hopefully we'll get to. We should hopefully get to. So 7 different types of normal disk that we can have. And our restriction was that every time our normal surface passes through a tetrahedron, it does so in one of these normal disks, one of these normal disk types. Something that is not necessarily clear from these pictures is that these 3 quadrilateral types all intersect each other. You cannot put more than one type of quadrilateral in a normal surface without self-intersecting. Okay, that's going to come up again later, is an important restriction on what we can do with a normal surface. So you can, the intuitive way to see why that has to be true, each type of quadrilateral cuts a pair of edges. So this edge and this one behind are being separated from each other, if you like, by this quadrilateral. And if you then try to put that over here, this one is cutting this edge from this edge, and so they're going to have to somehow cross over each other. If that doesn't intuitively make sense for you, stare at it for longer, but I don't know what to say. So that'll be that. Those are our types of normal disk. We're then going to say that we identify 2 normal surfaces together. We say that they are the same under normal isotopy, an isotopy of the manifold, which preserves the triangulation. We could get into a lot more details here. We don't need to. The idea is, so long as you can wibble the manifold around and leave the triangulation intact, that will wibble the surface with it, and we'll say it's the same normal surface. Yes?
Does that mean wiggling the manifold in a way that each simplex stays in exactly the same spot? Or does it mean wiggling and then the simplices are allowed to move as long as they don't like rip apart? Or
I think either is fine. You can, if you want to define it, you can say that it must leave the set of points that is the relative interior of each face of the triangulation intact. So like you can, like on an edge, you can sort of squish points towards the end, but the vertices have to stay in place, and the whole set of points must stay the same. You could also view it as just isotope the manifold so that the gluings stay the same, and I think that's the same as well. I'm getting a nod, so I'm going to say that's the same. So we have these normal surfaces. We want to somehow identify them because, again, the point was we want to write this down on a computer. We have to be able to represent the surface itself as well in the computer with some kind of data. The way we do this is with normal coordinates. Again, a bunch of words here. We are essentially just going to write down the number of triangles of type 1 in tetrahedron 1, then the number of triangles of type 2 in tetrahedron 1, etc., the number of quadrilaterals of type 1 in tetrahedron 1, and we continue. So we end up with a vector which is 7n dimensional, where n is the number of tetrahedra in the triangulation. So hopefully we can see, it should be fairly clear, I think, that given a normal surface, I can definitely write down this vector. I just need to go through, count everything, and we're good. The more important question, though, are they unique? Given a vector, does it represent exactly one normal surface? And the answer is yes, up to normal isotopy. So long as we identify, wibbling together, yes, that is a unique thing. That is theorem of Harkin. And then a slightly more thorny question, given a vector, do we know if it corresponds to a normal surface? Slightly more tricky to answer, but we can try and pull some more information out of the way we've constructed the object, right? So we can say every single time we have two tetrahedra which have an identified face, keeping in mind that given our rules, this could be the same to multiple faces of the same tetrahedron. That's perfectly fine. What's happening here is I'm identifying this face with this one, okay? And in particular, we're going to look at this edge for now. Every single time I have a pair of faces that I've smushed together, in order for my surface to be well behaved here, the boundary of the surface must only be in the boundary of the manifold, and that can't be on this face. So all of the components of the normal surface that reach this face must be matched by some component over here, which practically means that all of the triangles of type A in this tetrahedron plus the number of quadrilaterals of whatever type B, let's say, in this tetrahedron must match the number of triangles and quadrilaterals over there. In this particular example, we can see that we have a quad matching to a quad, triangle matching to a quad, and triangle to triangle. All of those are perfectly fine, so long as everything gets matched up. We don't have any stray bits of boundary floating around in the middle of our manifold. Yeah.
Question, so if I have this surface,
Mm-hmm.
how do I then get these vectors out of that surface? They have to compute these vectors regarding these normal surfaces.
Depends how you've represented it in memory, but the idea is literally you have sitting around somewhere a list of here are all of my tetrahedra. They have all of these different, like here's each vertex of each tetrahedron, and I've constructed my normal surface by writing down, I have put these triangles here and these quadrilaterals here, that sort of thing. You just count how many there are. If you just had one sitting in the wild, you would just go around, label each tetrahedron 1 up to n, and then count how many discs to each type. Algorithmically, but often in the reverse direction, which is what we'll see in a second. So what I get is a matching equation, every single pair of faces and every pair of edges on that face. Okay, so this only gives us 3 for this pair of faces because these are the same edge, right? So along this edge, I have those triangles. If I were looking at this edge here, I would need to count the triangles over here. We're just making sure we count everything up together. Okay. Okay, so matching equations. If we take all of the matching equations and we take a couple extra constraints, then it turns out that any vector which satisfies all those constraints does represent a normal surface. And because we know that it's unique up to normal isotopy from before, that gives us a effectively bijection between the set of vectors which satisfy constraints and the set of normal surfaces. Yippee. Bijection is great, but we still have an infinite number of these things. We can solve that, but that is infinite. I thought I had those the other way around. I don't think I need to say much more here other than we get a bunch of linear equations from matching equations. The quadrilateral constraints to make sure we're embedded is what I was mentioning earlier. We must have at most one non-zero quadrilateral coordinate for each tetrahedron type, sorry. Otherwise, we'll be not embedded, but that's enough. So long as we obey quadrilateral constraints and we obey the matching equations, and we're non-zero in every coordinate, we can't have a negative number of disks anywhere. That wouldn't make sense. We're perfectly fine. We do represent a normal surface. Yippee. Of course, that is still an infinite number of things, which is hard to enumerate. So if we want to be able to get all of them, whatever that means, we have to do a little bit more work. Namely, we want to define a couple of things. A normal surface is going to be fundamental if its representation in normal coordinates cannot be written as a sum of other vectors of normal surfaces. Okay? And further, it's going to be a vertex surface with a missing space if it is a vertex of the space which we defined slightly before. We get the matching equations. And this additional constraint where we sum everything to one. What that gives us is two different finite sets of vectors to look for. Because we only want, in this instance, we're saying everything has to be integers. Here, we're not going to get integers, but we only need to check a number of things which will scale up to integers. We may also need to check double covers, but asterisk, sweep that under the rug. We have, via these things, a finite number of stuff to check if we wanted to check all of the normal surfaces. Yeah.
Earlier you said that two vectors, so a vector, two surfaces with the same vector are the same. Is that way true as well? If there are two vectors, manifolds with two vectors, different vectors are the different manifolds, so can a manifold have two different vectors?
Different surfaces within the same manifold. But if I have two different manifolds and I'm looking at normal surfaces in this manifold and normal surfaces in that manifold, I don't know anything. You could get whatever. Yeah.
Two equivalent two manifolds, can they have two different vectors?
They could have no, it's unique.
It's one-to-one.
Yeah.
I mean, like, if it's unless it's like one vertex, you could have like I forgot the word, the thing where it's triangles around the vertex.
The vertex link. Yeah. Oh.
Like,
Yes.
in the sense that they're the same surface, but they're just completely elsewhere.
Yes. Sorry, that's a good point. Yeah. So vertex link is saying you have vertex, you just take all the triangles around it, you just get what should, in theory, be a sphere, whatever happens. You could have another vertex link at another vertex. They would be the same, like topologically the same surface, right? But not the same in the triangulation. So you could have that happen. What was that?
There's a lot of redundancy there as well, right? Like if you go through every vector division, that's more than their own surfaces.
Yes. More than around surfaces. So long as your vector obeys, I don't think there's meaningfully more. Like you could still, as much as the normal surfaces are telling you something about the manifold, they are also telling you about the structure of the triangulation. So I would argue that it's not really more, like you get as many as the triangulation gives you. You could, of course, have a different triangulation for the same manifold, and you can get different stuff happening because the structure of the triangulation is different. Evie was first.
On definition 2 there, is that going to be a normal surface? Normal surfaces have a whole number of.
Yes.
So do we actually mean like an element of that?
So what I actually mean here is scale up to the least integer multiple. Where least multiple where everything's an integer.
Right.
So take that vector, just scale by whatever you need to. So you get a vector of integers, and then you're good. So it turns out to work. There'll be probably some details in there, but yeah. Was a question? Yeah. Yeah, Gabe.
That whole discussion with Michael, all this kind of to say that the relation of isotopy respecting the triangulation and the relation of isotopy are different. I think Michael was more of the latter, and then we also care about the triangulation.
Yeah, you might care about the triangulation. You might only care about the manifold. But yes, I'm not quite sure I got the question, but okay. Cool. Okay, so the idea of what we have here is, yeah, we've got finite sets of stuff to look through now. And it turns out, in particular, that for many definitions of the word interesting, interesting normal surfaces come in one of these flavors, at the very least. Vertex surfaces, easier to enumerate, there are actually less of them. So if you get vertex surfaces, then you're all well and good. Fundamental can still be done, there's still finitely many to look for. So, hooray. In particular, I've somehow managed to duplicate that, there we go. In particular, and my examples run out, but I should do it on this slide. In particular, if you have a incompressible surface in your manifold, do I want to say compressible or compressing surface? One of them, and I cannot remember. If you have one of them, there exists one which is a vertex surface, vertex normal surface. If you have an essential disk or an essential sphere, there is one which is a vertex surface. So if all you need to do to check whatever property is look for one of those, then you just look for one of these. You just look for the vertex surfaces, and then you've got an algorithm for doing this, which just, sorry, let's rephrase that sentence. If all you need to do is search through all the vertex surfaces, then you've got a finite amount of work to do to check. Cool. So that gives us something useful. And moreover, if you wanted to, for example, see if a knot is the unknot, to use the example from earlier, all you need to do is embed that knot into S3, take the complement, take a triangulation of the complement, and then take the normal surfaces of that object. And if it's the unknot, you will find a disk which is the unknotting disk, the disk that would sit in the middle of your unknot. And saying it like that does display the fact that this is still a lot of work, right? You still have to do all of these steps, but that gets you an algorithm for recognizing the unknot. It might not be totally practical all of the time. There might be better ways of doing it depending on how you've got your information stored, but you can do it. And Harkin, way back when, was able to do it doing these things. Yes? That is, yes, that is very true. I cannot remember the detail of how you get around that problem. There you go. Perfect. Sure. Why not? Yeah, long story short, you can get around that problem. You can effectively get an algorithm, thanks to Harkin, which lets you recognize unknots. Incredible. You also get, thanks to Rubinstein, an algorithm not quite doing this, but using normal surfaces, which lets you recognize S3. That was later improved upon by Thompson, I think. But you get algorithms there. Someone by the name of Thompson. We wouldn't possibly know who, but someone. And then it turns out also that normal surfaces are just kind of useful. So, for example, Ktenidis invented them in a sense in order to prove this. If you have a compact orientable three-manifold, you can take a connected sum decomposition into prime manifolds. Hooray. And that was done by Ktenidis, proved that it existed. Milner proved uniqueness later on, but the origin of that is in studying these normal surfaces. So moral of the story then, turns out you can just take surfaces inside your three manifolds and study them to determine properties of your original manifold, which is pretty cool, pretty neat, and also kind of gave rise to computational topology in many ways as we know it today when we're talking about three manifolds. So lovely stuff there. That's as many slides as I have. So if we have questions, I'm very welcome to, I'm very open to them. And there we go. Yes?
Do the hashes represent the joins?
Yes, the connected sum between manifolds there, yeah.
Why don't
Yes.
you draw each other?
That's a great point. Yes, I absolutely should have had a picture of that.
I'll ask a question while you're drawing.
Yes.
Is the connected sum associative? Like, does the order of this matter, or can I just like do it in whatever? Like, if I have like three of them, do I need to do like M1, M2, and then M3, or can I do it in another order?
No, you should be. It's associative.
Does it
Yeah.
matter? Okay.
Yeah. So to do it, well, the example on knots is easy. And where am I going? This needs to. What have I done? Yeah, you're right. Okay. I have a torus, and I have another torus because that's the only surface. And if I want to take a connected sum of these two things, I'm just sort of cutting out a bit of the boundary and then gluing them together with a tube, if you like. And that has given me something that is the same as this. Cool. You can kind of see how that's the same surface in both instances, just by gluing two tori together. Yeah. They are subtly different things. There are exactly, if I remember, there are three manifolds which are prime but not irreducible. So subtly different, but modulo those two, yeah, you're fine. Oh, that's a great question. I'm not sure if it lines up. It probably does. Yeah. Yeah. Yes.
Do these normal surfaces then give us ways to compute invariance and stuff?
Invariance. That's a great question. Not that I can think of off the top of my head, but I'm sure there's probably something in there. I would have to look. Danielle, I think. What was that, sorry? 3D index. Ah, yes. There you go. So yes.
I'll try a few, yeah, I'll do function invariance. But then reverse more first.
Yeah. So at the risk of cursedness, yes, is I think the answer to that question. Yeah.
In terms of like the computability stuff, what kind of like question would you ask? Would you say like, can we take I don't know, factorial or three manifold? Are we interested in like computing this decomposition?
Yeah, you may well be interested in getting a prime decomposition of your three manifold. You could be, depending on where your data is coming from, like you could be doing applications, scary word for some people in the room, in which case you get something that pops out and you're like, I need to identify what knot type this is. There are probably sometimes better ways of doing it than this, but the algorithms exist. You might get some kind of higher dimensional manifold and you need to identify, well, you might just need to take a decomposition. You might need to identify if it has certain properties, and that can be answered by just checking all the normal surfaces for something. You'll find one that tells you if it does or does not have that property.
And just out of curiosity, like how, this is a really bad question, but how, in your own research, how much like have you seen people use like AI to do these sorts of questions? Like, is it very, are these...
Great question. Is this motivated by the news that came out this morning particularly?
Yeah.
Someone has allegedly, yeah.
S has a complex structure, maybe. Yeah.
Apparently there's a complex structure on S6. Not something I've looked into. I haven't come across it. It's very possible that it exists somewhere, but not something that I've seen. If you're looking to jump ship into a better field, I don't. No, not that I'm aware of. Maybe. While I think of it, just to actually go back to the question about phrasing this in terms of computability, the better way to phrase the computability side of this is saying, hey, you have if you have, for certain instances, you have just the vertex surfaces you need to check. One of them will be a certificate for either resolving the decision problem either in the yes or the no case, and and the certificate will be one of the surfaces. So just finding all the normal surfaces definitely resolves the decision problem either direction. So you have a finite number of possible certificates to check, which is useful. Yes, Mike.
So on a similar less depressing note, so if in the future I end up somehow in the land of manifolds, and I do some of the manifold reading, I want to know, and I want to know when I should look into normal surfaces. What is the flavor of problems that is, I guess, smart to, if I see this problem, okay, now I should be thinking of normal surfaces.
That is a great question I do not have a good answer to, I'm afraid. But Daniele might.
This decomposition here is also geometric, but the point is that this is prehistory, but Seminar sources work, which is use surfaces and all this stuff beautifully to see relations to geometric methods, especially for models.
By geometry mean what here?
Constant geometry.
So like somehow like RG or AG connections.
Yeah, 100%. And this is a very student musician where it was in all spheres. There's another one called JSJ, or composing angles of toric. It's also more or less unique, and each piece admits some geometric interpretation, some geometry, and that was sort of the preferred route to the concurrent conjecture, or the geometrization conjecture, which is the bigger one that there are.
And if I remember correctly, specifically, you can do JSJ decomposition also using normal surfaces specifically, yeah, rather than others. I didn't intend to. I hope. So true, so true. Christian's talk was dimension 6 and above. We're strictly below that, definitely here. There we go. Oh yes, also Higard splittings, very cool stuff. Was there a question? Yes, CB.
Is there an analogous construction, say, with 3 submanifolds of a 4-manifold?
Probably. No, never mind. I'm being told that there is not. Fair enough. Yeah. If there were to be, it would be so much more cursed. I don't want to know. Oh, yes, of course. Yes, you have that problem. So you'd be restricted in what you could work with in higher dimension. Cool. All right. We appear to have possibly run out of questions. So I guess we'll leave it there.